Here we go. All right. So today we're going to start chapter 8, which I think of as our last chapter, even though we're going to just dip into chapter 9 as well, 9.1 for multiple regression. But chapter 8 is called an introduction to linear regression, but let's just call it linear regression. Linear regression sounds maybe a little bit weird, but it's really just fitting a line of best fit. Okay, so for us, right, we're going to have a relationship, and I want to between x and y, usually visualized in a scatter plot. When I want to fit a line of best fit is how we call it. Oops, line of best fit. In high school and stuff like that, the line of best fit. And so I'm going to call these models. So we're going to be modeling this relationship. Okay? And so we fit these linear regression models to try to predict values. Okay? So linear regression So linear regression models the relationship between a numerical response variable, and then I'm going to say and an explanatory variable because it can be categorical, but most often it's going to be a numerical explanatory variable as well. And so just in general, and an explanatory variable. And this variable is often numerical. We can do it with categorical variables, but it's often numerical. So kind of going back to our roots, I think that door opens, right? Yeah. It's this one that locks, that one's open. So go back to our roots and we can visualize this relationship using a scatter plot. So we can visualize this relationship with a scatter plot. And I'm going to use the scatter plot in the textbook. Now, the way this is set up, and it's kind of a constant struggle figuring out how to introduce these concepts, because without the line pre-existing, we can't talk about how we generate the line. So we assume that we have a line, talk about how we would get the line, and then we know how to get the line. Right. And so it's kind of like, okay, well, we have a line, so how do we get it? It can be confusing, right? And so this example, just so we have some background on the brush-tailed possums are a marsupial that lives in Australia, and a photo of one is shown in figure 8.4. There it is. Researchers captured 104 of these animals and took body measurements before releasing the animals back in the wild. We consider 2 of these measurements, the total length of each possum from head to tail and the length of each possum's head, right? And so for whatever reason, doesn't really matter, some researcher was interested in this relationship, right? The length of the head, which is presumably kind of something like this, versus the total length. We suspect there's a relationship, right? Unless you've got really funny looking possums, some with tiny heads and their huge bodies, right? That kind of thing. We suspect there's a relationship here. So it's pretty reasonable. Not very interesting in terms of a question, but that's okay. That's what we got. Yeah. And so if we plot this data in a scatter plot, it would look something like this. And maybe I'll put it over here. You've seen scatter plots before, I'm sure of it, right? They even put scatter plots in newspapers and stuff. We've seen scatter plots in real life, but let's just remind ourselves that first off, this is the y-axis and this is the x-axis. That's going to be really important in terms of our calculations, right? And so we're going to be talking about x and y, and so those are going to be placeholders for the response variable is on the y-axis. Response, or the dependent variable. Dependent, okay. Variable goes on the y-axis. On the x-axis is where we put our explanatory or independent variable. So in this case, the total length we're going to say is the explanatory variable. So what we think is it can explain the head length, essentially, right? And so we can look at this thing and we see that there's some sort of relationship, right? So when we look at a scatter plot like this, we're going to want to be able to describe this relationship. Just like when we looked at a histogram and we said, okay, just eyeballing it, shape, center, spread gives us a good idea about the distribution, right? Same thing here. We're going to do it, but with a scatter plot. So to describe the relationship, between x and y, we talk about three things again. We talk about three things. First thing is the direction of this relationship. We have two options. It's either positive or it's negative. And so the direction, and like I said, we have two options. It's positive or negative. If it's positive, then maybe I'll use a slightly different color here. Trying to stay on this page here, x and y. If it's positive, it's going up like this. And if it's negative, then it's going down into the corner, the bottom right-hand corner. Just in general, right? Are things increasing together, or as x is increasing, y is decreasing, right? Those are only two options. So that's going to be good to know. The second thing that we talk about is the strength of the relationship. This can be a little bit finicky because it is so kind of personal. What do you see if you see a strong? So I'm just going to talk about strong or weak. You can throw in kind of descriptive words like moderately strong, right? Moderately weak, right? You can kind of go on a scale, but just in general, I'm just going to talk about a strong relationship or a weak relationship. So a strong relationship is something where you you can see clearly the relationship, right? In my mind, as soon as I'm able to see some sort of relationship, so for example, here, I can see there's this general relationship kind of captured, oh, that lower one was a bad one, captured kind of in this path, right? As soon as I'm able to see, I would say it's moderately strong, right? As soon as I'm able to see it, I'm going to call it strong. But then depending on how kind of wide it is, you would say moderately strong, relatively strong, that kind of thing. Or if you just call it strong, that's fine too. It's just to get a sense of the relationship. In terms of a weak relationship, that's going to be kind of on the most extreme end. It's just going to be a cloud of points. Was it weak? It means that it doesn't matter what value of x you put in, right? That tells me nothing about the y's, right? And in terms of a line, it doesn't really matter if you fit a line like this or like this or like this. They all kind of do about the same job, right? And so that's what makes it a weak relationship, when there's no kind of starting off point, I guess. The third one I can call the shape or the form. I like to use shape because that's from the histogram, right? Shape, center, spread. But we can call it the form of the relationship. And my two options here are linear or nonlinear. This course, we only focus on linear relationships. We're not going to talk about nonlinear relationships. And the reason for that is because even if you have a nonlinear relationship, you can often transform the data so that it becomes linear, and then you can fit a straight line. So the linear techniques kind of reign supreme. There are other models, of course, right? But that's for a later course. But for us, starting with the linear model is the most important one. Yeah. Linear, remember, means straight line. So if your line of best fit, when you just eyeball it, if it looks like a straight line, does a straight line do a good job of describing this relationship, then that's great. Or there's lots of different nonlinear relationships, but kind of a most obvious one would look like this. Essentially, if you fit a line to this, right, a line of best fit might go something like this. That doesn't describe this relationship. It does an amazing job of modeling those two tiny regions, and then it does a totally garbage job for the rest of the data, right? Because what we're going to do is we're going to use this line to predict values, right? So if I'm like fighting every urge to not just go here, but for recording reasons, so if I want to predict at this value of x, right, my predicted value would be on the line, but what actually happened is way up here, right? And so here, the difference between my line and my actual values is way too big, so it's not a good model. Just to kind of specify, and maybe here, so linear just means that the relationship is reasonably modeled with a straight line. Is reasonably modeled with a straight line. We're only going to discuss linear regression. Okay. we will only discuss linear regression So one of the main things to keep in mind is that all these tools that we develop assume that we have a linear relationship, right? So that's kind of our number one thing that we're going to look for. Can I use a straight line, right? If I can't, then we need to find other methods, right? And so, which means all the tools we are about to develop rely on having a linear relationship. This one's just for fun, but we can make a scatter plot, but that's boring. Let's see here. Where is it? Oh. Or you can make a scatter plot. If you look up the scatter plot package, they just give you the code to generate these scatter plots. You can use different cats for your points. Use all the same cats. I'm sure they've added cats. There might be colored cats. I haven't checked it out, but there's lots of different cats. And so, or make a scatter plot. People only develop the most important packages in R. It's like, okay, I can make a scatter plot, but can I make a scatter plot? There. So thinking back to the histograms when we talked about the shape, the center, and the spread, right? Same thing as when we said, okay, fine, we can eyeball it. We can look at, see where the center is, what the spread is. But then we develop numerical measures of center and spread, right? The mean and the standard deviation, for example. So now we're going to do the same thing for the direction and the strength of a linear relationship. So we're hooked on a linear relationship, and that's where we're going to be stuck. Okay? But that's totally fine. The correlation, you probably heard correlation before, you probably used it even, right? But the correlation is a numerical measure of the strength and the direction of a linear relationship. The correlation between X and Y is a numerical measure of the strength and the direction of a linear relationship. It's really, really important, and I guess have an R on there, right? That it's for a linear relationship. The problem and the reason we still have jobs is because a computer might not recognize that, hey, I shouldn't be giving you the correlation here because this relationship isn't linear, right? It's just going to do whatever you tell it to do, right? And so it's our job to look at the relationship and say, yeah, I feel comfortable fitting a straight line to this, right? And talking about the correlation in terms of the definition from the book. Oh yeah, I do skip ahead a little bit. Got my own flow here. oops. This is like the one, I try to use the same notation as the textbook always, so I try to be flexible, but the textbook uses capital R for the correlation, and I can't shake the lowercase r. So in terms of the definition from the textbook, the correlation, which always takes values between -1 and 1, describes the, and I'm going to add the direction and strength of a linear relationship between two variables. And we denote the correlation by capital R or lowercase r. I guess C was taken, or something else. I can't think of what C was being used for, but it's not for me to know, I guess. There are 2 R's in correlation though, so fair enough. And so in terms of our correlation, if it takes on values between -1 and 1, then it's centered on 0. It describes the direction, because if it's negative, it's a negative relationship. And if it's positive, then it's a positive relationship. In terms of the value, a correlation of 0 means that there's no relationship between these two, right? Things are happening willy-nilly. There's no relationship here. It's just a cloud of data points. And so here, and I guess I should use, so a correlation of 0 means no relationship between X and Y. A correlation of 1 or -1 is a perfect relationship. And of course, +1 is a perfect positive relationship. Oops, forgot the first word, perfect relationship. Right. All the points are on the same line. Right? Everything in between, as you move from no relationship, as you move out towards 1, right, the relationship becomes stronger. And just to have kind of a guide, and it is totally flexible, but just to have some sort of jumping off point, I would use 0.5. So anything between -0.5 and +0.5, I would call it weak, moderately weak, right, as you get closer to 0.5. So I'm using round brackets for a reason, right? It's very flexible, but just so you have some sort of guide, right? This would be a weak relationship. And then running out of colors here. Sure. Here, kind of -1 to roughly -0.5 is going to be a strong negative relationship. And same thing here, if it's positive, then it's a strong positive relationship. Rough approximations. There's an example just to show you the different correlations that I'll bring in here. Did not use the, just so you can see what these different correlations look like. Positive 0.33, right? I can kind of squint and I can maybe convince myself that there's some sort of relationship here, but it is a weak positive relationship. And we see that with the correlation, right? It's a low value, but it's positive, right? So then it's a weak positive relationship. This is what a correlation of 0.69 looks like. So you can kind of, from here, kind of figure out, okay, 0.5, that's probably when you start to see a relationship. So here, when I look at this, I kind of see a relationship. So that's why I use 0.5 as a guide-ish, right? Here, correlation's getting higher, so 0.98. Things are getting closer and closer together, which means what? In terms of predictions, it means that I'm going to have reliable predictions, right? That's a good thing. Okay. And then a correlation of +1 just means that they're all on a line, right? A linear line. That can happen, but for us, that's never going to happen, right? If you imagine you have this machine and you look at the output after running it for 1 hour, you got 4. I run it for 2 hours, surprise, surprise, I got 8 things out of it, whatever it's producing, right? And so then you've got this kind of perfect relationship, but that's not interesting. Why would we don't really care about that, right? We're more interested in kind of these guys, right? When there's no relationship here, there's not a lot of value in our analyses, right? Because we would have to say, oh, well, I predict that it's going to be this value. But it could also be completely different from that because I don't have a very strong relationship to begin with, right? Same thing, negative 0.64. So here we're starting to see that, okay, there's some sort of relationship here, and then it tightens up, and then you're at -1. Okay. So here, right, kind of, because I do find that people struggle the most with the weak relationships, right? It's easy to see when you have a strong relationship, but when can I say that I have a weak relationship? I would even say that this one's moderately weak, right? Moderately strong. Do those mean the same thing? I don't know. Right? So, right, but here I would say for this first one, I would claim to have a weak positive relationship. And I'm going to add linear relationship. Okay. Because I don't see any other shape, even if we don't know how to generate curves, right? X squared, x to the 3, whatever. We can make curves, nonlinear relationships. But even if we don't know that, I don't see anything better than a straight line to fit to this, right? And that's the thing that we're going for with the linear relationship. So like I was saying, what we're going to use these regression models for is to predict values. I'm going to call them future values generically. I don't mean future in time necessarily. I just mean unseen values, right? So things that I haven't seen yet, I want to be able to use this little bit of data to know what this relationship looks like in general, right? I want to be able to talk about all brush-tailed possums, not just the 104 that I have in front of me. So the most common use of regression is to use the model to predict, and I'm going to underline that because that's important. And I am going to use this term future because I kind of want to desensitize you to it. Oops, if I can spell it. It's not hard, future. But I will specify here, not necessarily in time, right, but unseen. If we want to talk about time, then it becomes a time series analysis. So my explanatory variable is a time variable. one thing that happens, and it's its own kind of field, time series analysis. And so we're not going to deal with that. Okay. But what happens is as soon as the explanatory variable is time, all your points are not independent of each other anymore, right? Which is one of the things that we're kind of not saying, but it is something that we're assuming. We're assuming that all these are independent of each other. And then when we introduce time series, now they're not. So we would need to deal with that. But that's for a different course. It's kind of a whole can of worms. Okay. But it's good to know and kind of keep in mind. So you want to fit a line? Well, you might remember the general equation of a line. Y equals mx plus b is a pretty common way of saying it in kind of high school situations. I don't know where that came from, the mx plus b. You could use a plus bx if you wanted to, right? It doesn't matter. So let's just recall the general equation of a line. Is y equals mx plus b, right? Or if you prefer something kind of crazy, a plus bx. Usually we use b0, b1, b2, b3 because we're going to be estimating betas. Beta is a Greek letter, right? I'm going to kind of gloss over that, but we are using sample information, right, to try to learn about the relationship in the population, right? So there's going to be sample coefficients, and then there's going to be parameters, so population coefficients that we're trying to figure out what they are, just like we did for means and proportions and all that kind of fun stuff, right? But here we get to gloss over it a little bit more. So the coefficient that's attached to the x, just as a reminder, because it is going to be really important, the coefficient of x is, of course, the slope. Is always the slope. As whatever's attached to the x is the slope. Then the coefficient on its own should have given myself, how about I do this? Bump it down one. The coefficient on its own is the y-intercept. There. So that's just in general, we need to be really fluent with reading the equation of the line, because we're going to be using them. And if you mix those up, everything's going to be wrong, right? And it won't make any sense. Like I said, for this scenario, we're going to start by saying, okay, here's the line. Let's see here. Where is it? So we're not going to talk about how we calculate the slope and the intercept today. We will on Tuesday. I'm just going to show you kind of the quick calculations, because of course R or Excel or whatever is just going to give it to you, right? But it helps to know if you've put things in correctly, what to expect. So that's why I want to do it. But so if we want to describe the relationship between head length and total length using this line, then we could fit this line, and we're just going to use it as it's given. And the equation for this line is y hat just kind of a new thing that we haven't seen before. Okay. Y hat is the predicted value of y. We've seen the hat before, but that was in a sample proportion, right? P hat is the sample proportion. These two worlds will never meet. And so we can reuse that notation, and in the regression scenario, it means something completely different, right? It means the predicted value of y. And so they're completely different, but by just context, you'll know which one it is. Because I don't want you to be thrown off and think, hey, where did this come from? I'm just going to make a note here. We're going to hold off on calculating these coefficients. So we will hold off on calculating, calculating the coefficients and use the given line for now. So in this case, it might be helpful to replace the x's and the y's with the names of the variables, right? Because then I find that it's helpful, right? Because if I have y was the head length, I think, let me just go back there, Caterplots, was the head length, and x was the total length, it's going to be so important. And I know it's basic, right, to keep track of your x's and your y's, right? But it's so important that you really keep track of them. Because now y was the head length. I almost had to go back up there. Was the head length, and x was the total length. So we can replace the x's and the y's with something that's from the data, right? So we could write head length hat. How do you read that? The predicted head length, right, is 41 plus 0.59 times the total length. Right? So then when I ask you, okay, if I find a possum that has a total length of 91 whatever units, centimeters, right? What's the predicted head length? That's a reasonable question to ask, right? So then what do? You say, okay, well, I was just told that the total length was 91. I can plug that in and I can solve for the predicted head length, right? And vice versa, right? If I tell you the predicted head length was this, what was the total length of this possum, right? And so here, 41 is our y-intercept. Usually I just call it the intercept. And the slope is 0.59. I'm going to hold off on the definitions of these because later I'm going to get you to interpret the intercept, interpret the slope, which just means apply the definition of these things, right, to the numbers. Okay, but for now, right, if I look at, I'm going to grab this one. So now that we magically have this regression equation, y hat equals 41 plus 0.59 times the total length, right? And so that is the equation that I have here. And for simplicity, I'm not going to use the variable names just because it gets too long and I'm lazy. But y hat is 41 plus 0.59x. One thing, you might be looking at this and say 41, hey, it doesn't cross at 41, but this is not 0. Nice. So, right, it's just an anchor. If you have a total length of 0, do you have a possum? No. So do you care about the predicted head length? No. Right. And so there are this line. The problem with the line is the line extends from negative infinity to positive infinity, right? So you can predict for any value of x, but you don't want to extrapolate. I'm going to introduce that next week, but you don't want to extrapolate beyond this range because it doesn't mean anything, right? I built this line using this range of x, so that's where it's valid. Anything outside of that is less reliable. So if, for example, just to jot down that, if I ask you to find the predicted head length, find the predicted head length of a possum with a total length of 91 centimeters. Usually we use these equations, right, or these regression models because x is easy to measure and y is difficult to measure, right? So usually we put in the effort for this data set and then we're able to use it for future. I mean, maybe it's hard to measure the head length, right? Maybe these things bite and you'd have to sedate each of one of them to measure the head length, but maybe it's easy to measure the total length, right? You have them run through something and you can just kind of take a snapshot, see the total length, right? That's kind of the scenario that I'm imagining, because otherwise, if you've got a possum and you can measure the total length, why not just measure the head length? But anyways, we don't need to pick it apart. We're just doing the math here. So we have our formula, right? Or the equation of the line y hat, which is the predicted head length, is 41 plus 0.59 times the total length, which is x. I want it to be 91 centimeters. 41 plus 0.59 times 91. You want to make sure that these units match up, right, with what your data had. Otherwise, you'll have to convert the units, but that's pretty rare that you have to deal with that. Just to show and emphasize the order of operations here, just be careful that you multiply the slope and the x value together first. That's like the number one thing I see. 53.69, which means the predicted head length is in millimeters. I was like, how's the total length 91 and then the head length is 94, but it's in millimeters. Phew, I was just talking about units. Almost bit me in the butt. There, millimeters. Phew. I've done something wrong and no one stopped me this morning. Can't blame them. It's pretty early. So for each value in our data set, we're going to be able to calculate the distance between the observed value of y and the predicted value of y. And we call that the residual, or the error of the model. So the distance between an observed value of y, between an observed value of y and a predicted value of y at the same value of x, so it has to be at the same value of x, is called the residual. The residual, or the error, I bring in the error because it's denoted by an E. R was taken, right? We just used it for correlation. So now we're playing this game of catch up. But in general, as soon as we're talking about a residual or an error, we use E. So in terms of the predicted value that we found here, 94.69, what we did, right, was we said, okay, here at 91, right, I put in an X of 91. If I kind of go up here, and I'm doing it by hand, so it's not going to be, I want to catch that X equals 91, but then my predicted value is here. I'm going to be able to find, and drawing it by hand's a bad call, but 94.69. Right. I have a predicted value at 91, but I also have observed values at 91, potentially more than that, right? But each point is going to have a residual. Okay? So the distances here are the residuals. How we calculate the residual, right? It's just in terms of the y's, right? I have some observed y, and then the residual, or the predicted value of y, and the residual is the distance between those two. And so what we do is we say, okay, E, the residual, is going to be the observed, oh, I'm skipping the i's for just for now, the observed value of y minus the predicted value of y. So this is the observed y minus the predicted y. Because I'm doing this for every point in my data set, each point is going to have a residual, right? I can use that value of x, I can plug it into my equation, I can find a predicted value, I can compare it to the observed value of y. So U, I. Okay. So you do that for each of them, right? And that's what so every point in our data set will have a residual. The methods that we use, right? And even if you were fitting this, so let's say you didn't have this line, what would your brain be doing? Your brain, if I asked you, just draw a line of best fit, how would you do that? Your brain would go, okay, it wouldn't say it like this, but what would it be kind of doing if you had to articulate it? You would try to minimize the residuals, right? Kind of intuitively, when we fit a line of best fit, we're trying to minimize those residuals, right? I'm trying to build a line that catches most of this activity, right? And that is what a line of best fit does. And so here, when we fit a line of best fit, how about I say when we draw, just kind of taking us back to, I remember in chemistry, we would kind of do these experiments or whatever. I would draw my scatter plot and then I would take out my ruler and I'm like, there it is. There's my line of best fit. And I feel really good about it. We're not going to do that though. But same idea. When we draw a line of best fit, we try to minimize the residuals. That's exactly what the official technique also does, right? The official technique that we use most commonly, and there are other methods, but I don't know, I see no reason to use other methods. This is the most common one, is the least squares regression line. So this is what the least squares regression line and maybe I'll say does as well. Right. It's a little bit more complicated, but in terms of kind of the least squares regression line, it's the most common technique. It's going to be the default in R. When you use the LM command, for example, it is the least squares regression line, linear model. Okay, and so if you wanted to use a different technique, then you have to search for it. But this one's fine. Well established, works fine. So what do we do? If I'm trying to minimize the residuals, then, well, what I could do is I could calculate all the residuals. And when you fit a line in R, it'll store the residuals. So it stores the predicted values so you can access them. You can store the residuals, right? And you can access them. So it's not something that we do by hand typically, but how it fit this line is it chose the line that minimized those residuals, right? But if it's the observed minus the expected, so all these points below the line would be negative residuals. All these ones above the line would be positive residuals. If I add them up, because of how the technique that we use, these errors or these residuals would always add to 0. So that's not very helpful, right? That's a fact. They would just cancel out, add to 0 because of how we fit the line. So the method that it's using in the background is, all right, if I'm looking at kind of the total residuals, I'm probably going to be summing them, right? It's reasonable. If I'm summing positives and negatives, right, they usually cancel out, so that's no good. So then our go-to move is to either square them or take the absolute value. We're going to take the square. There's a couple of reasons. The square, if you square a distance, then it amplifies larger distances, right? So it kind of makes adjustments for these bigger residuals. If you think about a residual of 2, let's say, right? If I square that, I get a 4. Okay? A distance of 3, that's only one more, right? But then when I square it, all of a sudden I'm at 9 and I have to deal with that 9, right? And so that's going to pull this line towards my residuals usually, but we'll deal with that next week. But so here, the least squares regression line minimizes the sum of the squared residuals. You could look at the absolute value, and that is a type of model that you could fit, but it's not very common because then you're not amplifying those larger distances. So we use squared values. For the first reason is that negative residuals become positive. Otherwise, the sum of the residuals would be 0, and that's a fact. Otherwise, the sum of the residuals is 0. But it's also to amplify large residuals, which is important to us. We use these residuals to assess our model, right? If I've built a model, I'm usually comparing it to other models, right? And so I've got these different models on the go, and I want to find the best model, right? You've worked with this possum researcher, and you're saying, I'm going to find you the best model so that your predictions are reliable, right? And so to assess our model, we do a residual analysis typically. There are other ways, but for us, it's plenty. To assess a model, we use the residuals to conduct a residual analysis. Our residual analysis is going to look at 3 things, okay, just kind of at its core. So a residual analysis, and maybe I'll do this. First thing we're going to look at is that we have approximately normal residuals centered on 0. We want to have most of our residuals close to 0 because that means our line is close to the points, right? And then we're allowing for some kind of extreme values on either end, right? But it has to be symmetric. How can we do that? I could make a histogram of the residuals. I could make a QQ plot of the residuals, just eyeballing it. So look approximately normal. We're going to look at linearity. Okay. So the residuals also have to follow a straight line, and it is completely linked to the original scatter plot. Okay. But that's why we use them, is because it's a magnification of the original scatter plot. Okay, it kind of shows you what's going on. So we're going to look for linearity in the residuals. And we're going to talk about constant variance in the residuals. one thing to remember is that these residual plots that we make are really just magnifications of the original scatter plot. Yeah. And so here, the residual plots are really magnifications of the original scatter plot. Oops. So where is this? Here. Just a couple of examples. The top scatter plots, those are the original scatter plots that we're looking at here. So here, these are the original scatter plots. And these are the residual plots. The residual plot is going to have the residual on the y-axis. And for our purposes, I'm going to say the x-axis is going to be the explanatory variable still. There are a couple of nuances, but for us, let's say here, you've got, I need more space here. So the residual plot is going to have the residual on the y-axis. And for us, I'm going to say we're going to put the explanatory variable here. Which means, right, and the reason I do that is because, okay, then this x-axis is going to be the same. Right? Notice how, and this really kind of bothered me when I was first doing residual plots. I would say, okay, well, I look here and I say, okay, it looks like a good model. And then I see it again here in this residual plot. There's nothing really happening. I was kind of confused. I'm like, okay, well, I see that that's not a linear relationship. I see even more so using the residual plot. But as long as you think of it as kind of, okay, it's going to just magnify and show you a little bit better that maybe a linear model wasn't so appropriate here, right? Because all of a sudden now we see that, okay, there's kind of some non-linear relationship there. And so each of these is showing a couple of things. First thing I want to say is that in a residual plot, what we're looking for is random scatter around zero, right? You want to have a normal distribution, so the residuals have to be normally distributed, centered on zero. All these residuals have to be around zero. And so usually kind of there's that line at zero, and we're looking for random scatter around zero, right? That means that you can assume that the residuals are normally distributed, right? So the first condition is met. It means that you have a linear relationship because your residuals are linear, and the constant variance is from that random scatter. Yeah. Right, because that means that, which means the residuals are normal, and by that I mean normally distributed, and you have constant variance. Here in this kind of second set of plots, what we're seeing is, okay, I don't have random scatter around 0, right? There's this pattern, a non-linear pattern, right? And so here, this would be a non-linear pattern, which means this model is not really that appropriate, right? It's going to have negative residuals for a portion of the data, positive residuals for another portion of the data, and then back to negative residuals. It just doesn't do a good job. The last one that's kind of tricky is the constant variance. So the constant variance is when we have something like, and I'll just use the red again, something like this. This residual plot, I don't love how this one worked out, but it's kind of a magnification of this kind of spray pattern. And I want to just show you a more extreme version of that one. So the constant variance, I guess really I'm going to be talking about non-constant variance. Or how about this? I'll draw them both. Constant variance is when you've got a center on 0 and you've just got kind of random scatter, which we said, and they're kind of within some realm, versus non-constant variance would be when we have something, so they might still be centered on 0. However, these points, right, might be really close, right? I'm just doing kind of a more extreme version of the one above. Okay. So here for this region down here, small residuals means that I have this very reliable prediction, right? So here I have reliable predictions up to this point in X, right? Because this is my X-axis, right? So up to some point in X, I have these really good, really reliable predictions. And then at some point, right, if I'm thinking about out here, I have extremely unreliable predictions, but we're not going to be able to communicate that in our model, right? And so we're going to need to make adjustments for this. But here we have these unreliable predictions. So that's where the constant variance condition comes from, is, well, I want to have the same kind of reliability in my predictions across my model, right? I don't want to have this kind of wishy-washy thing where we don't know that there's the difference, right? And we can't incorporate that into our model, or can we? No, that's not for us. So, good. I would argue that's the boring part of regression done and dusted. On to fun things next week. Quick calculations, interpretations. We're on easy street now. If you have any questions, let me know. Otherwise, see you tomorrow for the quiz. Stop this.